Hello there dudes, this is a follow-up tutorial branching off from model loading part 1 of my OpenGL Quick Start series. Tutorial 3 of that same series we downloaded and configured the GLM Maths library. We did produce some transformations, but I never explained how any of those transformations worked. I've put links to both of those tutorials in the description and a link to the source code for this tutorial. In this tutorial I'm going to demonstrate the difference between local axis rotations and global axis rotations by using GLM rotation matrices. I'll show you what that looks like geometrically and explain why it works the way it does, and then we'll finish off by using that understanding to apply rotations directly inside the vertex shader. I'm going to be using this model plane which I created in Blender, the 3D modelling software. Notice that I've got the camera set back out of the screen so that we're looking forwards at the centre of 3D space. Let's start by getting some rotation transformations up and running. Now, even though rotation transformations only require a 3x3 matrix, GLM rotate requires and returns a 4x4 matrix. That makes sense because we need to multiply our rotation matrices with the view and projection matrices, which are also 4x4 matrices, and the model translations that we'll be doing in the next few tutorials also require a 4x4 matrix. To get GLM to rotate our new matrix, we need to call GLM rotate, passing in our matrix, the angle of rotation and the axis to rotate around. We pass the transformation matrix to the vertex shader by calling GL uniform matrix 4FV. This is the uniform location as set on this line, and this is our rotation matrix. The code for drawing your model is this part, which we used in the model loading part 1 tutorial. This is the vertex shader, which is just the minimal code as we've used before, which I've also taken from the model loading part 1 tutorial, and likewise this is our minimal fragment shader code. Let's now compile the program and give it a try. There we go, it's rotating around the x-axis as it should be. I'll just now go through exactly what is going on so that we've got an overview of the steps involved. We loaded a model just here by calling the model class. We then set up the camera and declared the relevant matrices. We used GLM rotate to rotate our model matrix and GL uniform matrix 4FV to pass it to the vertex shader. These few lines of code then asked OpenGL to draw our model, which involves vertex shader processing followed by fragment shader processing. For each OpenGL draw call within the main loop, the vertex shader runs, typically thousands of times until it has completed processing all of the model's vertices. Our model rotation matrix is being used just here to rotate those vertices. Just before we look at what matrix multiplication looks like geometrically and why it works the way it does, let's create another rotation matrix, but this time we'll rotate around the z-axis into screen instead of around the x-axis. So now we can see it rotating around the z-axis as expected. GLM minus z is into screen and plus z is coming out of the screen. Now let's see what happens when we multiply the two matrices together. So clearly there's a combined axis rotation going on, but it's difficult to see exactly how that's working. Now let's change the order of multiplication by placing the matrix that is now on the right to the left side of the multiplication sign. So it definitely looks different, but once again it's difficult to see exactly what is going on. To explain then, the first example rotated the model around the x-axis first and then around the local z-axis, whereas the second example also rotated the model around the x-axis first but then around the global z-axis. Let's now add a few lines of code to control how long each of the two rotation matrices is being applied for, which will make it much easier for us to see what's happening. We can now see it rotating around the x-axis, and now because all three axes have become tilted by that same rotation angle, the rotation around the local z-axis of our model matrix is also tilted. But now once again, after changing the order of multiplication as we did before, although it starts off the same by rotating around the global x-axis, it then rotates around the global z-axis instead of around the local z-axis. Now why does it work this way? How can changing the order of multiplication produce a different result? What does the geometry look like when multiplying 3x3 matrices together? This is what a 3x3 rotation matrix looks like when we are rotating around just one axis, which in this example is the z-axis. If those two triangles look familiar to you, then it's probably from when you learnt trigonometry back in high school. You can see how this green vertical component comes into existence as the initial x value of the yellow vertex is rotated around the z-axis. Likewise, you can see how this red horizontal component comes into existence as the initial y value vector is rotated. This is what it looks like when we add all of those vector components together to produce the resulting vertex position. Now in principle, that is the entirety of what happens when we rotate points in 3D space, but when we rotate around more than one axis, those sine and cosine terms become multiplied together. So this animation is for rotating around the z-axis, but this is the matrix for rotating around the x-axis as we did before. And after following the rules of matrix multiplication, we end up with these two resulting matrices, which depend on the order of multiplication as we've just seen. This is exactly what we've just been doing by rotating the model plane. Watch how both of the green vectors first rotate around the global x-axis, but then one of them rotates around the local z-axis and the other around the global z-axis. Now think back to those two triangles which we saw existing as the geometry of z-axis rotation. This is what the geometry looks like after multiplying the x-axis and z-axis together. Let's just look at where the x component produced by the y-axis comes from. For the local z-axis rotation, it's simply the vertex's initial y value rotated by the z-axis rotation angle of 60 degrees. Notice how the x-axis rotation makes no difference to the result. For the global z-axis rotation, we have sine c times cos a instead of just sine c, as we had for the local z-axis rotation. As you can see, this looks the same in that there's a vector component being rotated 60 degrees around the z-axis, but instead of that vector component being the vertex's initial y value, it's the cosine of its initial y value that becomes rotated. This is how the geometry changes as we adjust the x-axis rotation. When the x-axis rotation is 0, the geometry of local versus global rotation is equal, but as we increase the x-axis rotation, we can see how it changes. Finally, let's look at the z component value. For local z-axis rotation, the value is dependent on both x and z rotation angles. But for global z-axis rotation, the value only depends on the x-axis rotation, which is the very reason why the length of the z component vector remains constant as the vertex continues to rotate around the global z-axis. So now let's take advantage of us knowing how this all works by rotating the plane directly inside the vertex shader without us even using any rotation matrices. Now we do need to pass a continuously increasing rotation value to the vertex shader as a uniform, which is because shaders don't retain state from one draw call to the next, but we can simply pass our existing counter variable since that's already being incremented. Let's copy the APOS input attribute to a new vec3, which we'll call newPOS. So all we need to do to transform the vertex position y and z values is use the exact same for sine and cosine terms as we just saw being used for x-axis rotation. And we do the same thing for the normal vector y and z direction values. We normalise the vertex normal as usual, and the only thing we need to modify for GL position is we remove the rotation matrix since we aren't using that anymore, but then also change apos to new pos. Now let's compile and run it. And as we expected, we've got the plane rotating around the x-axis, and just for fun I'm going to mess with the trigonometry a little bit to see what bizarre effect it might have. And yep, that's pretty bonkers. The only other thing I want to show you for this tutorial is that we don't have to rotate around perpendicular axes. So let's undo all of what we've just done so that we're back to using matrices again. And now let's change the rotation vector so that we have it pointing in some arbitrary direction. That worked, but let's now comment these two if statements so that it rotates continuously. Please give us the thumbs up because it really does help, and don't forget to subscribe. Cheers.